Welcome. We're going to do question 96 and 97. Let's do that. So question 96 states, a study of a performance of computer printers and printing time for 22 small text files were recorded. So it looks as if I'm two quantitative variables. So that means I better write the formula for my least squared regression line. So once again, if you are taking notes, I hope you are, I'm reading this question and I'm saying to myself, this is a two quantitative variable, which means I have a least squared regression line, which is going to help me predict. If I know x, I can predict y. So we write down the formula, y hat is equal to a plus bx. And we know that this is the constant, also known as the y-intercept, and that this is my slope, and that's x. Now in this question, we zero in on these words right here. They did us a favor. They did the entire study for us, and they have a printout. So it is our job to put this piece of information in our formula here. The constant is our a. It changes not. A constant means it doesn't change. So notice the variable a doesn't have a rate of change because it's just the same number. So the location of the graph on the y-axis would be that. And then 3.47812 times x. So we build the equation. From this equation, y hat is whatever I'm trying to predict, plus the constant, plus my slope times x, size. So I write the word size here, and then looking up in my problem, it says this is print time. So I'm seeing in this question, I can predict print time if I know the size in megabytes of the computer printer. Now, looking at the question, it doesn't have anything to do with this, so I tricked you into reviewing that. Oh, I'm so mean. They want you to do an inference about the slope. So we can do an inference about any piece of data we pick, and it looks like they did some type of a confidence interval, a 95% confidence interval, so I'm going to copy that formula from my formula sheet. It says the formula for a confidence interval is the statistic plus or minus the critical value times the standard deviation of the statistic. And this isn't a sample mean, this isn't a sample proportion, it's a slope. So I need the standard deviation of my slope, and this is just my slope. The statistic is the slope plus or minus the critical value times the standard deviation of my slope. So a 95% confidence interval would be equal to my slope plus or minus the critical value times the standard deviation of my slope. There it is. Take those notes. Now we're diving into the problem here, and we say to ourselves, oh wait, I know the critical value of a 95% confidence interval. I think it's this number, 196, that I get out of this table, B. B is in boy. When I go to table B, and I look at the number 95 at the bottom, the number right above there is 196. However, I only get to be down here if I'm a proportion question. And this is no proportion question, my friends. This is a mean. So you actually have to be up here. And you look at these degrees of freedom and you say to yourself, how many degrees of freedom do I have? So when I zero in on the question here, I noticed they were nice and they calculated that for me as well. And the reason why it's not number minus n is because, remember, we have two quantitative variables. So 22 minus 2 is 20. So looking at my critical value from the table and scooting over from 20, that's where I get this number, 2086. 2086. 2086, bam, bam, bam. I've eliminated everyone but A and D. Now I'm digging a little deeper. I've got the critical value right. The critical value is 2.086. What's the slope? And notice this is marking down the statistic. So the statistic has to be the slope. And remember, we found the slope already is 3.47. So this is my slope, so it has to be A. Now you might be thinking, okay, so I got the question right, but where's this number? What if they ask me that number on the test? I look up here in the problem, and remember, this is your slope. What was this number over here? The standard deviation, also known as the standard error. There it is. That's the standard deviation of the slope. So take some notes with me if you could, please. This is the slope. This is the standard deviation of the slope. And once again, this is the intercept. So I'm going to write that on my paper. And I'm going to go to the next question. Next question. Not a lot of people miss this. Let's read. It says, which of the following statements should not be included in the summary? So that means all of them would be okay to be in the summary, except one. So one is different than the others. Let's take a look. It says a study of existing records of 27,000. So immediately these are existing records, and we're supposed to be realizing at this moment this is an observational study, not an experiment. They collected data after the fact. So there was no isolation of variables. And so when we have, let's write this down, observational versus experiment. When we make observations, or we study observations after they're happening or while they're happening and not really getting in the middle of it, then that's definitely not an experiment. Okay, so we say to ourselves, why would that really change things? Well, here, when you observe, you have no idea what other confounding variables are happening. Here, and not all of the time, but some of the times, if you isolate almost all of the variables, you can actually do cause and effect. So, what did they study? They studied whether or not if someone was wearing a seatbelt and if they got in an accident, but that happened after the fact. So knowing that it's happening not in the present tense, but past tense also helps you realize this is definitely an observational study. So what happens in observational studies? Well, the driver's behavior might be a confounding variable, and that's true. The child's location in the car might be a confounding variable. Totally agree. The study was not an experiment, so cause and effect is not warranted. So all three actually go alike. All three are basically assuming that these are observational studies, and therefore observational studies run the risk of lots of confounding variables, and because of those confounding variables, we can't use cause and effect. Now I'm going to jump to E. It says, concluding that the seatbelts save at least is risky, at least until the study is independently replicated. So when I independently replicate something, I'm taking something I observed and I'm trying to recreate it in the setting of an experiment. And that's once again saying the same thing as the three above. This is basically saying I can't say cause and effect. It's too risky to do that. I can make some observations and then replicate it in an experimental setting. Then and only then could I say cause and effect. Therefore, our answer is D as in dog. Thanks for joining us.